Hello. Today we are going to discuss about the Bayesian models, the Bayesian learning and its fundamentals that can be used in machine learning. Right? This is a way of thinking, a somewhat different way of making predictions or making inferences in machine learning, which is somewhat different from the earlier techniques that we have learned. So we are not going to discuss in detail, in depth, how the Bayesian models are used in com in contrast to the other models that we have learned before. But we are going to discuss about some of the models that Bayesian techniques are used. But in in a bird's eye view, we will see how we can understand the the conceptual differences in the Bayesian method compared to the earlier techniques that we use, which are known as frequentist approach. And Bayesian methods are actually very accurate. We will see why they are good, better than the frequentist methods, and why we are going when we are going to need it, and why we are not widely using these techniques as well, right, at the moment. But we will definitely use these techniques uh, in wide usage when we will have much computation power in the future. Uh, Even now, when we are using uh, heavy computation power with techniques like neural networks, uh, we can actually use Bayesian approach for neural networks as well, although we are not using, but in future they may also become popular. Right. So before that, first let's see what is the main philosophical difference, or the thinking pattern difference in Bayesian thinking, right? Compared to the traditional way of thinking. Right? So when it comes to making predictions, that means making predictions means making probabilities, right? So when we are predicting the probabilities of an event, so that is what we are doing in machine learning, right? So in when making these predictions, or when find or estimating the probabilities for a particular event, there are two schools of thought, right? So one school of thought is known as frequentist statisticians, or their uh, way is known as frequentist statistics, and the other school of thought is known as Bayesian statistics, who are Bayesian statisticians. So in the statistician uh, world, there are two types of people who believe in two different schools of thought based on the philosophy of taking the probabilities and or making estimations uh, based on these two schools, right? So we are not going in detail how these things are, how each of them are different, but we will see the main differences in their schools of thought, right? So when it comes to frequentist statisticians, so how they make probabilities is that, for example, if they want to find the probability of having heads in a particular coin when you flip it, right? So their approach is, they say that if you want to find the probability of having heads in a particular coin, you have to throw that coin, say, like 50,000 times, and then you can, so 50,000 means a large number of uh, times. That means with very high frequency, with high count, and then you can find what is the proportion, what is the uh, proportion where it goes for the heads and which proportion will come for the tails, right? So that is the frequentist approach of finding the probabilities of finding the probability of having heads in a particular coin, right? So that means they have to run the test again and again for a long run, and then we have to come to the statistics, right, to find the probabilities. But in contrast to the frequentists, the Bayesian statisticians are somewhat different, right? So what they believe is that so they when they want to predict something, or they want to have some probability, how they think is that they say that whatever we believe now, that means, so when we are believe means we are assigning some probability, right, for a certain event. So when you are making some predictions with a certain probability, that probability is affected not only with the given data, but also the prior belief probabilities, prior believing probabilities of that particular person, right? So, so that may sounds like not relate like a concept which is not relevant to scientific way, right? Where we take our own personal prior probabilities where what we believe, right? But when it comes to Bayesian statisticians, so they don't say that we have to come with our own probabilities as priors. What they say is that in some way, not on it's actually a belief, but with some way we can come up with a certain prior probability. That means, for example, when I say that I want to predict the probability of having the heads in a particular coin, so by nature sometimes we think that yeah, this kind of coin may have a probability of 50-50 for having heads and tails, right? So in that case, if that is our belief, that is known as the prior, right? So we take that prior probability into the equation where we start with these prior probabilities, and then with the new evidence, where when we do the experiments, that means when you flip the coin again and again, and then when we get the observations, then we can update the prior probability so that it would go to the real value, right? So with large number of coin flips, it would if the coin is a biased coin, so it may have some different probability, right? If not, it would, if it is unbiased, it would still be 50-50, right? However, so we start with prior, so we take account into our previous probability, previous uh, beliefs in the probabilities into the account when it comes to Bayesian way of thinking, right? That is the difference between the frequentists and statistics. The frequentists say that we have to do the experiment for a long time, and then we have, that means for a very high number of times, and then we have to get the probabilities. The Bayesians say that uh, we may not be able to do it many times, but we have to start with the our previous assumptions. That means the previous uh, knowledge about the probabilities in that particular event, and then we can apply the new observations, new evidence into the equation, and we can get the probabilities, right? That is, these are the two main differences between frequentists and Bayesian worlds of statistics. So for example, so let's take it two examples where the frequentist approach would like when it comes to medical research. So they have, the frequentist would say that we have to uh, take the results based on the frequencies after taking the medicine for a large number of patients. The Bayesian would say that we have to look at the previous research or the previous studies that were done on that particular or similar kind of research, and then we can use these existing probabilities, and with new knowledge or the new experimental evidence, we have to update the probabilities of the success rate of a particular medicine, for example. So the Bayesians are thinking from the previous probabilities. So in the cultural way, we can say like having prejudice, right? So we start with the prejudice, and with the new evidence, we change our prejudice uh, with the new evidence, right? So that is how the Bayesians do. Frequentists have to start from a clean ground, right? It's like and they need a lot of data to come up with that. But in practice, frequentists are also using these kind of uh, corrections in their calculations known as hallucinations. So we will not go in detail, but Bayesians are explicitly telling what they are doing. Like for example, when you are adding the previous probabilities that we already believe, they do it with their theory, Bayesian theory. But however, the Bayes theorem is a theory that is believed by both frequentists and Bayesians without any conflict. But the Bayesians are mainly uh, using the Bayes theorem for making the predictions based on the some previous priors, right? Prior knowledge. The frequentists are doing the similar kind of thing, but in a different way. Right? That is the difference. So, so let's take another example, right? Like, so when, for example, if you say that if it is going to rain today, right? So this is about the Bayesian thinking, right? Uh, so when you hear that the weather forecast says there's a 70% chance of raining today, right? So this is the what the news says in the about the weather forecast. So it says that there's a 70% chance of raining. So we can take this as the prior belief, right? That means we take this as the probability, this 0.7 as the prior probability. And now what happens is you go outside and you see there are dark clouds in the sky, right? Which is the new evidence, right? Okay, now you can update your probabilities, right? Maybe it's your new probabilities may become 80% or 90% of uh, about the chance of having a rain because you start with the prior belief that where there would be a rain in 0.7% or 70% using the prior knowledge that you gain from the weather forecast, and with the new evidence which is related to dark clouds, you having you looking at dark clouds, you see that there's a high probability that there would be a rain in upcoming minutes or hours. So you can update the probability of having a rain starting from the prior and update these probabilities into a much larger value, right? Larger probability with the new evidence, right? So by looking at the when it is raining uh, and the probability of seeing the dark clouds is known as the likelihood, right? So, so that is opposite of what we are going to look at, right? So in here, what we are going to see is that when there are new clouds are there, what is the probability of having a rain, right? That is what we are going to estimate. That is known as the posterior, right? Posterior probability. That is what we are going to plan, what we are going to predict, right? But uh, when it comes to having the probabilities of having dark clouds when there are rains, when it is raining, what is the probability of having dark cloud? That is known. That is the uh, that is the opposite of from seeing a crane uh, given that there are dark clouds, right? So which is the opposite of the uh, posterior probability, right? So that is known as the likelihood, right? So using the likelihood and the prior probabilities, which is the weather forecast probability, you can predict the posterior probability, which is given the dark clouds are there, what is the probability of having a rain? Right? So this is what the uh, Bayesian statisticians do. Right? Take the prior knowledge, prior probabilities, and use the likelihood estimations, and you can predict the uh, posterior. That means the later probabilities based on both likelihoods and prior probabilities. Right? And the new evidence. Right? New evidence means we have seen a dark cloud. Right? So in very simple terms, I have given the Bayes theorem. So I have used different colors for each of the uh, concept that is described in the Bayes theorem, where you can see that in Bayes theorem there are so this is Bayes theorem is the backbone of Bayesian statistics, right? So actually the guy who named Bayes has found this theorem, but it was named by his name, not by him, but long term after his death. Uh, the person named Bayes has thought that this theorem is not that important. It is something very obvious, but the later statisticians have found that this is very uh, cool. That means this is kind of inspiring, and this can make inferences that are not obvious. Right? So we will see why this is not obvious, and this is very deep when it comes to making predictions, and why it is more smart at making predictions that are counterintuitive, right? So with so the Bayes has found this theorem, but it was actually made into public, and it was used widely by the statisticians like Laplace and so on. So its name was also given by other people, right? Not by himself. So this is a theorem. You might have learned this or not, right? So what we are going to find here in this Bayes theorem. So there are several forms of um, defining the Bayes theorem. So this is the one of the most famous way of uh, interpreting the Bayes theorem, right? So in here, the red color one, which is known as the given the probability of uh, ha having the event A given the event B has occurred. So this is what is this PAB is denoting, right? Probability of event A happening given that the B has occurred, right? So this is known as the posterior probability. So now let's look at the uh, orange probability, so which is the opposite of the posterior probability, which is given the seeing the evidence of so what is the probability of seeing the evidence B if A is given, right? So which is the opposite of A given B. This is B given A, right? Both are conditional probabilities, right? So this orange color one is known as the likelihood. Right? So in order to find the posterior, you have to use the likelihood, right? And this is the blue color one, PA, which is relevant to the prior. Right? Prior means the earlier probabilities that we know, right? Or the assumptions of probabilities that we have before we do this calculation, right? Or initial belief, which is known as the prior. So PB is relevant to the probability known as evidence, which is less used in these calculations when it comes to our classifiers. So you don't have to worry that much about this probability, right? So this is known as this is the probability of having evidence. Sometimes we don't consider this value, but we take this posterior is proportional to the likelihood than the prior, right? Sometimes. So we are not deep in deep take going too deep into these Bayesian theorem and its application, but we will try to understand the basic concepts of this Bayesian theorem and Bayesian learning, so that you will have some good background to start learning with this way of machine learning. Correct? So when it comes to Bayes theorem, so there are the main intuition is that you start with the prior probabilities and we change our beliefs based on the availability of new evidence. Right? So that means when you don't know anything, by just looking at one or two examples, one or two evidences, you don't come into a conclusion. Right? You should start with your prior probabilities. That's what it says, right? For example, when it comes to a very dangerous situation, for example, if you suppose you are going to the forest and you have heard that the lion is a dangerous animal. So lion is dangerous is something we already know, right? So we have heard it. So that is the prior probability that the lion is dangerous. So then you see that the lion is eating an animal, right? Hunting an animal, and then your probability of estimating that the lion is dangerous gets increased, right? So anyway, we know it, but even before we have seen by our eyes that the lion has eaten an animal or hunted the animal, uh, we have our own previous knowledge, right? So this previous knowledge is very important. So that is what we say, right? So when you see the previous, when we start with the previous knowledge and with the new information, our probabilities get updated, right? That is only what we do. So in order to see the effect of the Bayes theorem, so we will look at a small example, right? So when you say that we are starting with our previous knowledge and we are updating our knowledge with the new evidence, that seems very obvious, right? Right, like Bayes himself has thought about his own theorem, but when it comes to the real world application, sometimes we find that these applications are not obvious, right? Sometimes we can have some hidden unintuitive, counterintuitive results as well from the Bayes theorem, right? So that is what we are going to see here, right? So in this example, we will see about example where a patient has done a test for the particular disease known as the disease X, right? So he has done a test and he has given that the results are positive. That means he was infected with disease X, right? So what are the given data? The data given is that the first thing is that only 1% of the population has disease X, right? So that is one of the information that you have, right? And the other information that you have is that the test is very accurate, so that if the patient has a disease, the test correctly identifies it with 90% confidence, right? That means the probability of test being correct if the patient has a disease is 90%, right? So if you have a disease, this uh, test would show it would diagnose it correctly with 90% probability, right? If the patient does not have the disease, right, so the still the test would correctly identify them as disease free with 95% of the time, right? So you can't assume just by looking at this 90% number, you may think that, oh, so this test may be having higher number of false positives. That's why this test is very successful. So maybe the test may not be that successful, may not be that accurate, right? But in this statement, it says when the patient doesn't have a disease also, it says that there's a 95% of probability that it would identify that the patient is not having a disease, right? Now you are in bit trouble, it seems, right? Because it seems that the test is very accurate, right? Not only for identifying the disease itself, but identifying the disease-free cases as well, right? With 95% accuracy, correctness, right? The problem is, what is the probability that the patient has a disease if that test has identified him as positive? Now he was diagnosed as positive from the test, right? So what is the probability that he would have the disease, right? So now it seems, so if you are that person, you would be, maybe you would think that you are highly, you would highly, there would be a very high probability that you would have the disease, right? So you would be be scared, right? So with Bayes theorem, let's see whether your uh, scaredness or your fear is justifiable, right? What is the actual probability that you would have the disease when you find that your test is like 90% correct of identifying the disease cases, and when it can identify 95% probability when there are no diseases, right? Okay, first with using, when you are using the Bayes theorem, so we can find these you can follow these steps one by one, and you can come to the conclusion, right? The first step is that you have to find the prior beliefs, and then you have to find the new data or the evidence. And third step, you have to find the likelihood, and that's a calculation. And with all these three uh, calculations, you can calculate the posterior probability, right? So which is the probability which we are going to find. So that this is the answer for your question. We are the posterior probabilities is the probability that when the test says that you have a disease, what is the actual probability that you have that particular disease, right? So first step, we find the prior belief, right? So what is the prior belief? So you know that 1% of population has the disease X, right? So the probability of having disease X is 0.01, right? So for further calculations, you can calculate the negation of that, right? So of probability of not having the disease X is 0.99, right? So you can keep these two values in your mind, right? Okay. Now let's go to the second step. So that is about finding the new data or finding the evidence, right? Uh, so when the test say is diagnosing, right? Uh, there are the uh, information, the probabilities related to the test, right? So this we are the sensitivity is 90%. Sensitivity is if the patient has a disease, the test correctly identifies there's a disease in with 95% probability, right? So the specificity is 95. That means if the patient does not have a disease, the test correctly identifies them as disease free with 95% of time, right? With 95% probability, right? So we might have learned these terms earlier, right? Sensitivity and specificity. So there are the applications uh, of these terms in this application, right? Okay, and we find that the test results comes back positive, right? So test result says yes, you have disease, right? So these are the new evidence, and then you have to calculate the likelihood, right? So you want to know the likelihood of getting positive results given there are two possible scenarios. So this is how you calculate the likelihood. So we will see how the exact likelihood calculation happens, right? If the patient has the disease, that means if the disease is there and it is positive, the probability is 90%. Right? If the person does not have the disease and likelihood is 1 minus specificity, which is 0.05, which is no disease and positive. Right? So now we can have to calculate the posterior probability using the Bayes theorem. Right? So Bayes theorem says this is what we have already seen, right? In the colored image, in the colored notation, the beginning, this is what we have described earlier, right? Where it says, so when you see it is the when the test says it is positive, what is the probability of having disease X, right? So this is the posterior probability, and this is the likelihood. So likelihood is the opposite of this, which is positive, being positive, where the disease X is already there, right? So that means diagnosing positive when the disease X is there, right? And this is the prior disease X. This is the prior probability, and divided by the P positive. This is the evidence, new evidence, right? So now we do the calculations, right? When there's a disease X and it is positive, and there disease X and it is positive, it is 0.9, right? The probability of having disease X is 0.01, right? Which we have already seen, right? Probability of having disease X is 0.01. So then, so in order to calculate this one, the evidence term, which is the order probability of testing positive, this has to be calculated like this, right? Yeah. So if you think it in a way of probability tree, you can understand it, right? For example, the being positive is that you are having the disease X, and given the disease X, what is the having positive result, and having probability of not having a disease, and given there are no diseases, what is the having positive outcome, right? The addition of these two probabilities is the probability of having positive outcomes, right? So if you are not clear, just show me what I say, right? So there are two cases, like which is disease and not disease, right? Right. So just relevant to this part and this part. So having disease X and having disease X and having positive one. So let's have positive this one, right? So, and also there can be possibilities that you are having negative results, and you are not having disease and having positive results, and not having disease and having negative results. So what we want to have is the probability of having positive results, so which are relevant to this term and this term, right? So this is captured by this relationship, right? So you can substitute the values that we have already captured. We are having positive, and given the disease X is 0.9, right? And probability of having disease X is 0.01, and given there are no diseases, having positive results is 0.09, right? It, 0.05, I guess. Let me 0.05, right? And probability of no diseases, that is 0.99, right? So when you do the calculation, you will get the probability of 0.0585. Right? This is the n positive. Now this one is also there. We have already calculated this one is there. Disease X is there. So then you can do the calculation like this. So this is the posterior probability by multiplying this one, and then disease X, which is it should be 0.01, I guess. Yes, should be 0.01, right? 01, and divided by positive probability of positive, which is 0.0585. So the final probability would be 0.1538. So which is equal to 15%, 38 probability, right? Right. So after the positive test results, yeah, let's after the positive test results, the probability test that patient has disease is about 15%, 38. Right? So even though the test is very accurate, where you would have very high uh, probability, 9% probability that you would have positive results when you are having the disease, and when you are not having the disease, it would give the 95% accurate results that you are not having the disease. But still, just because uh, the probability of having this particular disease in the population is very low, right? That means because you are having a very low prior, now you will find that the probability of you get having that particular disease is very low, right? Which is 15%, right? 15% means less than 20%, right? So which is that means it's very low, right? So you don't have to worry that much, right? So being a healthy person is uh, highly likely than having this particular disease, although the test is highly accurate, right? So when you hear the results of the test, if you were the patient, you would got scared, right? Because you know the accuracy of the results, accuracy of the test, but still, because the probability of having that disease in the population is very low, you don't have to worry that much, right? So that is the power of priors. Right? When you know the probability of priors, if it is somewhat significantly different, so your final probability, which is the posterior probability, would be somewhat different, right? So you don't have to worry that much, right? So now you can do maybe another independent test for the same disease and use this probability as the prior probability and do the test again, right? So if that is the case and that particular result test is also accurate, and then if it also says that you have the disease, then it may be having a very high probability that you have the disease, right? Because now this is the prior probability, right? Not 1%, right? So that is how the Bayes theorem can be used for estimating the probabilities when it comes to real world application. So when it comes to Bayesian, right? So we will say that when it comes to all the, so we say we take these probabilities like the prior probabilities, posterior probabilities, and evidences, all of them as numbers, right? But actually, you can take the probability distributions or calculating the posteriors, right? So when you have the posterior, when you have the prior distribution, something like this, right? And if you have evidence something like this, then you have a posterior, which is having a much higher probability, right? But with lower variance, right, than the prior beliefs, because uh, of the evidence, right? So that is the value of Bayesian theorem, right? Where not only you get better probability estimation, but also your probability distribution would also get uh, a narrower range or narrower dispersion when it comes to its distribution, right? When you are having more and more evidence, and when you are using your prior belief to calculate the new posteriors, right? Actually, this diagram is not related to the scale that we have, what we have seen in the previous calculation, right? So this is just an example distribution, right? So this is not anyhow related to our uh, previous calculations related to the disease X, right? So this is just a representation. Okay, so with Bayesian updating principles, what you have to take into your mind is that there are several things, right? So the first thing is the prior matters, right? So that means when it comes to the prior, you have to find some have a good prior, right? So if it is possible, and it would diminish with the new data, right? And if it would refine the beliefs, when with the new data you refine the beliefs and go to a new probability with more and more evidences, right? And posterior is the balance. That means how uh, how the posterior probability is the balance between the prior beliefs and how consistent the new data is with the hypothesis, right? So you are using new data and the prior probabilities and get the hypothesis, right? And when it comes to the initial stages of the uh, evidence, when you are having a little amount of evidence, your uncertainty can be reduced a lot using the prior probabilities, right? That is one of the advantages of using Bayesian techniques, Bayesian probability calculations. When you are having less amount of evidence, you can use the uh, higher information, right? So unlike the frequencies where you need a lot of data, with Bayesian inferences, you can take a very highly accurate probabilities using the prior beliefs, right? So this is very useful because when you want to do some real world prediction, actually we know a lot more about this particular event, right? So we have a lot of previous information, right? So for example, if you want to predict the price the uh, of gold or something, right, in next month, right? So you can have the probabilities of having a world war in next month. So what is the probability of having the Federal Reserve rate cut in US dollars in next month? And you can find what is the GDP growth in the global markets in next month. What would be there are several many factors that you can predict, right? So which may already know, right? So you can take these previous probabilities into this into that into the equation, and then you can have a better estimate for probability than just using for example, if you are using a uh, candlestick charts or some price charts, just without just using the machine learning outcomes of from the previous price values, you can use the previous evidence that were already there, right? That we already know, and take these priors also into the equation so that you can have a better price forecasting, right? So similarly, so there's a famous uh, application of using Bayes theorem when it comes to finding the missing submarine, right, in USA, where they couldn't find where the submarine was disappeared. So with using Bayesian uh, theorem, so this is a very famous example of using Bayes theorem. So statisticians could find with very lesser amount of time, right? With the sensor information that they get from their naval vessels about the location of possible locations of the submarine, which was disappeared. Then using these Bayesian techniques, they could uh, shortlist the locations that the possible locations where the submarine would have ended up. So they could actually find the location of the submarine with significantly lesser amount of time, right? So if you watch in the YouTube, you would find this particular incident, right? So this that is why we can use how we can use Bayes theorem. Uh, Although it is sometimes people say that we are using Bayes theorem for making inferences even by humans. Actually, we are using the Bayes theorem, right? So when you are judging something, you use your previous knowledge, right? So that means we are, as humans, also using the Bayes theorem for making predictions, but there are certain things like in the earlier example, as we have seen, where when a test result becomes is said to be highly accurate, then we try to believe that the result is highly accurate. But given the previous data are highly low in probability when it comes to the when it comes to having a disease, then our estimations would be highly different, right? So in these cases, Bayes theorem can be used mm, to have some to have probabilities in a rational way, right? So in similarly, when it comes to machine learning, also when it comes to regression classification models, also the Bayesian theorem can be used, but sometimes because it is computationally expensive, they are not that much used. But when it comes to machine learning, we will see the overall idea where we are using the Bayes theorem for machine learning. Right? So this is an example of using the Bayes theorem for uh, machine learning. But in this case, you would find we are using a much simpler version of Bayes theorem, right? So the reason is that when it comes to predicting the uh, class label, for example, right, given the X data, right? So if this is a classification problem, it would be like we want to have the class labels given the X values, right? So if that is what you want to predict, so in the world of frequencies, what they are using is known as the maximum likelihood estimator, right? So although we haven't discussed it, so in that case we can simply calculate it, right? But when it comes to uh, the Bayesian world, right, uh, it's somewhat different. So right, maximum. So that's known as the maximum a posteriori estimator, right? So we are not going to discuss them here, right? So in that case, we are using not only this posterior directly from the likelihood, but we are using the prior probabilities, right? So in order to calculate this one, as we have seen in the Bayes theorem, you can use this likelihood, right? It's the opposite of C given X. The likelihood is X given C, right? So in order to calculate the X given C, that means to calculate the likelihood, you would actually, if there are the number of uh, X or number of features in X is so large, you would have to calculate a lot of calculations known as the uh, well, you have to calculate the complex joint distribution of all the features of x1 to xn, so which is very difficult and not practical in most of cases, because one is that it's computation expensive and the other one is that you don't have enough information, the data samples, to calculate these probabilities, right? So because of that case, it is not practical some cases, in most of the cases, when you're having a lot of X features and not enough data, right? In that case, if you can make a much we can say it's a constrained assumption, right? So if you can assume that these x1 to xn classes are independent, right? Not classes, these features are independent, then you can you can simplify this this Bayesian calculation, right? So that is known as the naive Bayes, right? So actually, what we are doing is, given the class C, if x1 to xn are independent, right? So it is known as conditional independence, right? So because given C, right, given the class C, if x variables are independent, which is known as the conditional independence, then you can you don't have to calculate joint distribution of features, but you can simply use multiply uh, the probabilities of having each of the feature, right, given the class, right, and you can take the multiplication of them, right. So this pxc can be also expressed in this form as well, right? C, so p x1 x2 xn given c, right? So this is same as this one. So this can be simplified to this way, right? P x1 given c times p x2 given c times p xn given c, right? Because you can multiply these probabilities because these conditional probabilities are independent, right? Because of this conditional independence, you can simplify this likelihood estimator, sorry, this likelihood, right, into this format, right? That is, when you can simplify this format, it is known as the naive Bayes, right? So in order to do that, your features should be conditionally independent, right? However, in real world, we know that our features are not independent, right? So always there are dependencies, right? But when it comes to certain applications, use you can apply this assumption and use this naive Bayes assumption, right, and apply it, and you can get very good results, right? The one example is that when you are using large number of features, right, like words in an email, right? So words in an email may be limited to like 200, 300, 400 words, right? But the number of features, that means number of words, possible words in the vocabulary are maybe like 20,000, 50,000 and so on, right? In this kind of scenario, uh, this naive Bayes assumption may work uh, sufficiently well, right? So when it comes to machine learning, we are more inclined towards having much higher practical value, right? So although they are not that much independent, in this kind of applications, you can have much higher accuracy, right? So in the email, so when it comes to uh, making a binary classifier, where you are trying to classify spam emails from non-spam emails, right? So given the class which is spam, you can see the words like cheap, buy, now, these kind of words. So these are the words, right? So x1, x2, xn, x1, x2, x3, right? And so you, because you are making the assumption that when it is given as spam, you assume that the probability of having each of the word with is independent, right? Because of this assumption, you can multiply the probabilities like this, right? So when given it is spam, what is the probability of having the word cheap? Given it is spam, what is the probability of having buy? Given it is spam, what is the probability of having word now, right? Because each of the probabilities are independent, you can multiply them and you can calculate this likelihood value, right? When you calculate the likelihood, you can simply calculate the posterior probability, right? That is what we want. That means we can find what is the probability of that particular email being a spam, right? So you can calculate this one. So now let's move into the problem of this naive Bayes classifier, right? So we have learned about regularization, and so which is because happens because of the we have to do it because of the overfitting, right? So when it comes to naive Bayes classifiers, let's see whether we are having this overfitting problem, right? So we find that when it comes to uh, the practical application of naive Bayes classifiers for classifying spam emails, for example, where you are using words as the features, right? So that means the feature set is relevant corresponding to the vocabulary of words, right, in the English language, right? When in that kind of scenario, right, the vocabulary is generally like from 20,000 to 50,000, right? So in that kind of scenario, so you can see how the feature count is very high, right? So when it comes to this number of features, like for example, say your feature count is 20,000, and your email has like 200 words, right? In that kind of scenario, most of the words are having zero probabilities, right? Actually, using this naive classifier, you can use the word counts or the probability of seeing each of the words in the email as the probabilities, right? So uh, not the seeing the word itself, but you can see the frequency. You can use the frequencies of each of the words in the email to to make these features, right? Not the words itself, but the frequencies. That means the count of words in the email, right? In this kind of scenario, you will see that most of the uh, frequencies are equal to zero, right? Because most of the words are in the vocabulary are not there in a given email, right? Uh, because of that, when you are calculating this value, right, pxc, sorry, it is given like this, right? So it's given like this, right? So if some at least one of the x is zero, what happens is when you take this multiplication, if one of the frequency is zero, for example, say this px2c is zero, so then this multiplication, the whole multiplication will become zero, right? So because we know that in email, most of the words would have zero frequencies. In that case, highly with very high probability, you would have a probability posterior probability of zero in all the time, right? So now that is the problem, right? So when your xi is zero for any of the xi, then this whole value will be zero, right? So this posterior probability would be zero, right? So having this problem, right? That means when uh, because this model is trying very hard to predict, right? That is the problem, right? So which is known as the overfitting problem, right? This because this one is having because this naive Bayes is trying to is having very high level of standards. When something is zero, it's going to become zero, right? So that is a problem of overfitting, right? So if you can ask the model to be much softer, right? So then maybe you would not be able to have zero values, right? So maybe having some other values, you'll see. In that case, you can actually uh, get some reasonable value for this probability, and you can use this classifier, right? So that is why the regularization should come into the play, right? So as we already know, regularization is a way of using um, of reducing the overfitting, right, or reducing the variance problem. Right? So in when it comes to naive bias, there are three main techniques that can be used for the regularization. One is known as the Laplace smoothing, which is also known as additive smoothing, and the other one is known as Lidstone smoothing, which is a generalized form of much developed form of Laplace smoothing. And the third one is using the feature selection dimensional reduction, which we already know, right? So let's first think what is this Laplace smoothing is. So the problem that we have when it comes to taking this this counts is that this frequencies is that particular feature is having zero frequencies, right? So just look at the, without looking at these red colored numbers, just look at the black color notations, right? So here what we see is, uh, so uh, this is not the posterior, right? So this is the likelihood that we are going to calculate, right? So for that particular uh, feature or that particular word, right? So this is relevant to this kind of, this is similar to this kind of probability, right? Which we are considering here. So it can be calculated by count xic, which is the number of times the feature xi or the word, that particular word appears with the class C, right? In the training set. That means, so when it comes to spam, what is the frequency of that particular word appearing uh, in an email, right? So count C is total number of occurrences of class C. That means class C is spam, right? Total number of occurrences of class spam in the training set. So how many spam emails are there, and how many words, how many xi word is uh, there in the whole data set, right? By taking this count, if this count is zero, right? So for example, if you take a very rare word, right? Say like mathematical term or something, right? Or Laplace or something, for example. So because Laplace is not a commonly used term even in 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 most of the emails, right? So maybe if you take a word like Laplace, it would definitely have a count of zero, right? In your data set, it would not be there, right? So in that case, this one becomes zero. That is the problem, right? So in order to avoid this becoming problem, if it becomes zero, what we can do is we can add a one by our mm, uh, with this smoothing technique, right? So with this Laplace smoothing, what we are doing is we are adding these two red color parameters, red color numbers into this equation, into this calculation, right? So instead of just using the number of words in the data set, we add one for each of the each of the word, right? So even if it is zero, there would be one, so this probability would not be zero, right? And also for the count also we add this v, which is the size of the feature space, right? Like the number of unique words in the test classification task, right? So if it's a test classification task, it should be if it's a spam classification task, it will be a number of unique words, right? Like it's like the vocabulary count, right? So so you use the vocabulary count and add one at the top, and so that you would have a non-zero probability for xic, right? So then you can calculate the likelihood, and then from the likelihood you can calculate the posterior probabilities, which is what we want. So this Laplace smoothing is all about adding one, hard-coded one to numerator of the feature, right? And for the denominator, we add uh, the size of the feature space, right? Is the uh, number of unique words, right? So, but the problem is sometimes this one may be too much, right? That means when it comes to very rare terms, right, this adding a 1 may be too much, because in some cases, even for the uh, non-rare terms, like ordinary, when you are having less amount of data, right, this 1 is a very large value, right? That means if you have like a few number of data samples, few number of spam emails, most of the words would that are there, right? So not the rare terms, but the frequent terms would also be having numbers like 1 or 2, right? So adding 1 would be a huge difference, right? So for very rare terms as well. So in that case, you can add maybe you should add a lesser number, not the 1, but a number between 0 and 1, right? So in the Lidstone smoothing, it's an improved version of Laplace smoothing, where you are adding a positive constant which is between 0 and 1, uh, and for the bottom you multiply this feature space count by alpha, right? So you can select a certain value for the alpha depending on your requirement, right? So this is a kind of hyperparameter where you have to select, right? So when the feature space is very large, right, the one would be aggressive, when you want to apply small corrections. That means you don't need a very large correction bus, but just you don't want each of these probabilities be 0, not very high values, but even a very low value is okay, right? So in that case, you can use a very low alpha value, right? So you would have a very low probability, not like 1, right? So when you're having some certain counts, you would be having very high probabilities, right? Which would not be hugely distorted by this number 1, right? So you can have a very small value, like for example 0.1 or something, and you can multiply this with this 1 also to uh, apply the same change for the denominator as well, right? And you can reduce the smoothing, right? So by adding 1 in the Laplacian smoothing, what you try to do is a form of regularization, right? So if you want to reduce the regularization effect, you can use alpha, which is a number between 1 and 0, and you can tune the regularization level, right? So as we have discussed earlier, we can use feature selection and dimension reduction to reduce the number of features, right? So when you reduce the number of features, you can get rid of the rare terms, rare words or rare features, so that you can have better performance, right? So you would not have the problem of having 0 probabilities. So that is another technique that you can use, right, for uh, for purpose of regularization. But in general, we don't call these feature selection and dimension reduction as regularization techniques. But when it comes to naive, you can actually use these two techniques for regularization, for achieving the regularization kind of requirement as well, right? So for dimension reduction, you can use PCA and LDA, latent digital calculation technique. However, when you have a very large feature space like vocabulary, it would not be practical to use principal component analysis, right? So these are the somewhat theoretical ways that you can use to reduce the features. But you can, depending on the scenario, you can use whatever the way. Either you use feature selection or feature engineering or some dimension reduction technique to reduce the number of features, so that the low probability features are removed or changed or something like that, right? Okay, so when it comes to the Bayesian techniques, uh, you will find naive Bayes is the most widely discussed machine learning technique in Bayesian learning, but there are other many other techniques as well that are inspired by Bayesian theory, right? So for most of the machine learning algorithms, even the ones that we have learned, you can do them using the Bayesian assumptions. Like, for example, instead of using a single value, you can use the distributions, and by learning with distributions, you can have new distributions. That means uh, in the ordinary machine learning, when you are talking about a single value of prediction or classification, when you are using Bayesian techniques, you would be dealing with distributions where you the the mean value or central tendency value uh, would be represented in this particular value, but there's a variance and there's a distribution as well, right? So when it comes to distributions, you would have the with the machine learning also you would get the parameters values which would also be distributions, and when you are making predictions, those predictions would also be distributions, not single values, right? So when it comes to Bayesian techniques, the advantage is that because you are having probability distributions, but because not you are having single values, when it comes to making critical decisions based on machine learning, you can use these distributions to make inferences. Like, for example, say you are having two models that are having mm, two different accuracy levels, but if these accuracy levels are maybe the average accuracy levels, right? So if if the A model is having a little bit higher accuracy than the B model, but if A model has a very high variance, maybe you should go for model B, right? Although it would have a lesser accuracy, it would have a very low variance. Because of that, you may select the model B, right? So there may be scenarios like that when you are making decisions. In that case, you can use Bayesian learning for this kind of critical decision making, like medical decisions and financial decisions, military decisions. When you are taking these kind of decisions, you have to think about distributions as well, right? So, so based on this Bayesian theory, there are several models that are developed. So some of them are as here, right? Like Bayesian network, also known as Bayesian belief networks, right? And there's a form of linear regression known as the Bayesian linear regression, where we are using the Bayesian concepts for linear regression, right? And there are ways of having training neural networks using Bayesian theories, which is known as Bayesian neural networks. And when it comes to mm, speech optimization or function optimization, there are Bayesian techniques as well, right? So we will, other than so Bayesian neural networks, we are not going to discuss because we haven't covered these topics. But when it comes to other topics, we will discuss each of them and look at little bit in each of them to have some understanding about the Bayesian application. So when it comes to Bayesian networks, they are graphs basically, where there are no cycles, right? So they are directed graph. There are no cycles, so which are known as directed acyclic graphs or DAGs in simple, right? So in these graphs, there are random variables in each of the nodes and the conditional dependencies in between each of the sorry, connecting each of the nodes, right? And each of the node would have a table known as the conditional probability table, right? Like this, right? So when you want to calculate the probability of a certain event, which are dependent on these some other nodes, you can use this graph to calculate the probabilities using the Bayesian probabilities, or the how the conditional probability works, when it comes to, for example, in this case, if you want to see the event of uh, seeing wet grass, there's a probability that it has rained or the sprinkler was turned on, right? And both of these uh, probabilities, these events would be affected by another random variable known as having a cloudy sky, right? So the cloudy sky would be affected for turning on the sprinkler or not, or it would have the effect of having rain, right? Or similarly, you can make a simple graph like this, and you can use the conditional probabilities, and you can update this table. So there are a lot of ways that you can use Bayesian networks, right? So those are so this is a way of this is a theory that you would learn in a probabilistic graphical method, right? Where you can draw graphs like this, and there are many applications that you can use these graphs, but we are not going to discuss in that much here, right? So in this case, so this when it comes to this kind of graph, you can calculate the conditional probability tables, right, for each of the nodes and make the probability inferences. Something like, what is the probability that it rained if we observe that the grass is wet? Right? This is a conditional probability question that you can ask. You see that the grass is wet, and then you ask what is the probability that it has rained. So with this network, so this can be answered by this probability, right? The grass is wet, G equals yes. Then what is the probability of raining? With this graph, you can actually calculate the probabilities uh, uh, which has happened, right? Because this is a graph, you can use the prior knowledge, prior probabilities in the other nodes, right? So when you want to calculate this probability, you can use the prior probabilities by using these CPTs, conditional probability tables, to calculate the probability of wet grass using the Bayes theorem, right? So these kind of Bayesian networks are used in a wide variety of fields like disease symptom models, where you can find the relationship between diseases and symptoms to find the probability or likelihood of having certain disease. And you can use this for financial risk management, like when you are trying to provide a loan for a certain person, then you can uh, draw this kind of Bayesian. You can maintain this kind of Bayesian network and find what is the probability that particular person would uh, pay that particular loan in time, or whether he would miss it, miss the premium, or the so what would happen, right? So whether it would become bad debt or something. What is the probabilities? You can calculate using the prior probabilities in the graph with much high accuracy, right? So this is another application of Bayesian network, and you can, when you are using visual applications mm, like before the deep neural networks has come, even after with the deep neural networks, actually you can use this. With the Bayesian networks were highly used before the deep neural network era. So there, where you can use the cameras for identify certain objects, and with each of the objects, you can actually create a Bayesian belief network, and using these probabilities, you can have what is the probability of having an obstacle on the road, and then you can take decisions on that. And when it comes to Bayesian theory, so another application of using Bayesian machine learning is Bayesian linear regression. So we have learned about linear regression, where you would have uh, when it comes to simple linear regression, you would have a single line. When it comes to multiple linear regression, you would have a hyperplane, flat hyperplane, right? Linear hyperplane. Mm. But when it comes to Bayesian linear regression, you are so actually it would not provide not a single line, but distribution of lines, right? And the values that you can predict are also in a normal distribution where you would have a mean value of B transpose X, right? This is what we have. This is what we predict in linear regression, right? So in the linear regression, we predict a single value, but in this case, we are having a linear regression where the mean is beta transpose X, and there's a variance as well with the variance of variance. So we will not be discussing that in detail, right? So this is we have used this uh, matrix because you are having different values, right? And that is why this I is used. And this posterior distribution of a model parameter is conditional on the training inputs and outputs, right? So when you want to find the posterior probability distribution, given the x and y values, you can find it like this, right? So using the linear regression. So we will not go into detail into the linear regression, right? So when it comes to Bayesian techniques, actually you can there's a natural regularization happens with these because you are using the priors, right? So this should somewhat avoiding the overfitting, right? And so we should regularize or shrink the para model, right? And also, so when because this is a distribution which is given by the base by the Bayesian model, so each of the parameter, like for example, if this is a simple linear regression, you would have the intercept, slope, and there's a sigma or the variance, right? So each of the parameters would also have a distribution like this, right? And also when it comes to um, the values predicted, you would have a distribution like this, where when it comes to the ordinary least square predictions, you would have one value, right? As you have learned, but this value in this distribution, ordinary least square prediction would be the maximum value of this distribution, but base posterior prediction or the value that is predicted by the value distribution probability distribution predicted by this by the Bayesian model, which is the posterior prediction, would be this blue color distribution, right? Not a single value, right? So using this, so if you want to do further calculations, further machine learning, you can use these distributions again for as inputs for another set of models, right? And you can generate another set of distributions when you are using Bayesian learning, right? So the advantage is that when you are having high confidence, you would be having a very low variance in this distribution, so you can make sure that your uh, prediction is highly accurate, right? Uh, Compared to the OLS, ordinary least square, where you would not be sure how accurate this would be, right? So with Bayesian learning, you can not only get the value but also the accuracy level of that particular result, because you are having a distribution but not a single value. Okay, so now let's move into the last uh, machine learning technique that we are going to learn with Bayesian learning, which is Bayesian optimization, right? So Bayesian optimization is actually used for optimizing expensive to evaluate functions, right? So expensive to evaluate means something like this. Say you have a function where there are many number of x variables, right? So if, when it comes to the optimization, suppose you want to find the uh, minimum value of this function, right? So in order to find the minimum value uh, in by using algorithm, you have to check sorry, to check different x values, right? And you can go to the uh, you can find the x values that are having least amount of y value, right? So, but if this is a small, if there are 1 or 2 x values, so this should be easy because you can, with a computer, you can have different values set to that particular function, and you can predict the values, right? Say you have like 1,000 x values, right? So when it comes to that kind of case, there would be lot of values that you have to test. So if the number of x variables are 100, the dimensionality of this particular space is 100, right? So in 100 dimensional space, uh, looking at each of the uh, space, each of the points in the space is very difficult, right? So in that case, you can't calculate all the values, all the nearby values using a grid or something, right? With using, so when it comes to 1 or 2 parameters, you can use grid search or something, or random search. But when it comes to many number of dimensions, it would not be possible because computationally practical, because uh, you have to do a lot of computations with the number of where the number of computations that you have to do exponentially increases with the number of dimensions, right? So if you want to take uh, 10 samples from each dimension, if you have 2 dimensions, you have to do 100 grid points if you want to search, right? If you have 3 dimensions, then you have to do 10 to 10 to 10. That means 1,000 data points you have to evaluate. If you have 4 dimensions, you have to evaluate 10,000. Right? If you have 100 x values, then you have to evaluate 10 to the power 100 number of grid values, which is not practical at all, right? So in that case, you can't uh, evaluate all the values in the grid. Right? Then what you have to do is you have to evaluate some values. You have maybe the values that you have selected randomly, and when uh, you find that in certain spaces there are much more information in it, and you find that means in this space you would find that low number of low value for that particular y variable, so you can search more into that particular subspace only, right? It's like suppose that you go to the real universe, right? So you are going to find the where the gravitational field is maximum in this universe, right? If you go to the sky, to the uh, outer space, and if you try to find, it would not be easy, right? So if you find random locations, and for example, if you find that particular stars, black holes, and so on, you would find that at certain black holes, you would find a very high gravitational field, and you can search only on this around this particular neighborhood, only around the uh, space of black hole. Then you would find, oh, now you find uh, there's a high gravitational field, and you can further look into the points around the black hole and see at which point where the probabilities, where the gravitational field is highest, right? Actually, it's a so it would not be practical. So I am just telling it for just for an example, right? So that is how we do in the 3D space. But when it comes to like n-dimensional space, that is the same way that we have to do, right? So in that case, we select some values and we find which of the values are having less number of y value, and then we can search around these particular y values and search around it, right? Only a small neighborhood around it and look around it, and then you find that in that neighborhood also in certain spaces you would have lesser amount of y values. Then you can focus on to that particular uh, space and look further, right? Like zooming in and in again and again recursively, right? That is what we do with these kind of optimizers, which are heuristic optimizers. We are not looking at all the places, right? So this Bayes optimization is that kind of optimization where you can uh, zoom in into these kind of locations in a heuristic way, right? So in that case, what we do is in mathematical terms, we are not going to discuss how each of them is done. So basically, in big picture, what we do is in order to find where we should focus more, that means we want to have a probabilistic model, right? Say like when you find there are certain spaces that you don't have to look into detail, you don't have to evaluate these values, right? Because your computation power is limited. You have to only look, you have to only evaluate the data points where you think that the probability is high, right? So for that you can have a so the original function is known as the objective function, right? So what the Bayesian optimization does is it makes a probabilistic model, which is known as the surrogate model or the response surface model, to predict the areas, right? Uh, so which should where you should predict the probabilities where the probability of having good results, right? So we will see see with an example how this would work, right? So and also you have to find a function known as selection function or acquisition function, which would select the next best possible location where you in the space or the data point where you should take the where you should evaluate, so that you can uh, look further into the model, where you can further update the surrogate model with the probabilities and continue the algorithm, right? So what you do is first so we'll see what would happen, right? So first you have to find the surrogate model, you have to define the surrogate model, and where you would find the probabilities uh, based on the data that are given. So you can find using the Gaussian assumptions. You in most of the cases you can predict what are the probabilities that you would be having to look into these particular spaces, right? And with the selection function or the acquisition function, it can predict in which data points that you have to evaluate, and you can do this algorithm again and again, so that you evaluate only the most required or highly probable areas, or highly probable regions, highly probable data points in the space, and then you can zoom into it, right? And you can run this algorithm as long as you think that it has come to a solution, to the optimum point where you can select a stopping criteria like the maximum number of iterations, right, to limit the computation power, or the time budget, or the convergence to a sufficiently good solution where the optimization error is the cost is reduced or something like that, right? And you can stop it. So let's because you may not have understood it very well, so we will take an example. We would omit the mathematical concepts behind it, so we will just see how what really happens in a big picture, right, in this Bayesian optimization, right? So for example, so we will take the example of hyperparameter tuning requirement in machine learning, where you can see we have already learned that you can use grid search and random search and so on for Bayesian for hyperparameter tuning, where you would have it is very computation expensive when the number of hyperparameters are high, right? So the hyperparameter is something like learning rate, right? So what you can do is you have to use a function where uh, you have to have an optimization algorithm where you should balance the exploration and exploitation, right? So these are two concepts that are generally learned in reinforcement learning, right? So the exploration means trying new values, right? So there are two things that you can do in the algorithm, right? Which are opposite for each other's objective, right? So actually you need both of them, exploration and exploitation, where exploration means you are trying to find new values, right? Find new values. Find, that means you are trying to explore more in this objective function, right? Uh, and sorry, uh, yeah. So and exploitation is focusing on promising values based on models predictions, right? So and that means either you can use your energy for looking at the learning in the about this algorithm, or you can use the existing knowledge to dig deeper into an optimum solution uh, with the existing information, right? And go to a solution, right? So for example, if you find that your local minimum is something here, if your minimum would be somewhere here, with exploration you would try to go for other locations and find there are other better minimum locations. But with exploration what we do is exploitation, what we do is we try to use our energy not to look into other locations but to optimize with the knowledge what we have already found and come to a solution which may become an which can become a local optima, right? With exploration you would go to different locations to find better optimum positions, but you would waste your computation power and time, but you would not waste that energy for you would not use your energy focusing on a particular point where you go for the optimum solution, right? Because you are just exploring the function, right? So you need both exploration and exploitation for a good solution, right? You may not come to the optimum global minima, but you would come to a good solution if you are using the exploration and exploitation in a balanced way, right? So say that now you are using this hyperparameter meters root mean square error score, right? So root mean square error is square root of mean square error, right? So we use this root mean square error score as the objective function, right? Objective function score, right? So suppose this is the one which we can't see actually at the beginning of the algorithm, right? So if we know the algorithm, if you know this function, you can simply go to this location and finish it. But because we don't know, we are trying to use this algorithm, Bayesian optimization algorithm, to find the minimum value, right? So suppose this is the value. So what happens is, what we have to do is we have to take, because we can't take samples from all of these locations because it is expensive. We can say take like 10 samples from the objective function, like this black circles, right? And we can continue the algorithm, right? So then what happens is we use the surrogate model. So with these 10 data points, we can make a surrogate model to approximate the objective function, right? So now we don't know the real, this yellow color line is the real function, objective function, but we don't know it. We only have these black circles, right? Using the black circles which we have evaluated with these 10 data points, we can create a surrogate model, right? So something like this blue color line, right? We think this may be the surrogate model, right? And if we are using Bayesian uh, theories, right? So you can use if you are using Gaussian distances, right? Probabilities, where you would find that near each of these data points that we have evaluated, the probability of variance is low, but right, in between each of these measured values, but in the areas where there are no measurements, you find there's a very high variance, right, or standard deviation. So this is the, so this blue shade represents the deviation which would be possible, right? So now what we do is what we try to do is we want to measure another value or the 11th sample from this uh, model, right? So what we want trying to do is we trying to uh, run this algorithm further and find a better solution. So we are trying to find the location of the 11th sample. Where should we take the 11th sample, right? For that we can use this selection function, right? Or the acquisition function, which is given by this green color, right? So this selective function or acquisition function will show the probabilities of taking the, what is the probability that you should take a measurement or evaluation at in each of the data points, right? So with this probability distribution, you find at this point the probability is maximum, right? So in this particular point, we can draw this red data point and we can evaluate this particular point, right? So now with the model, it's hard to evaluate. We evaluate in this particular point, and then you can update the surrogate model again, because around this data point the probabilities would be reduced a lot, right? And then you can uh, recreate the surrogate model, and then you can again apply this acquisition function one after the other and until you are satisfied, right? And then you can come to the you could find the minimum value or something, right? Minimum roots mean square error, and then you can finish it. So this is, after this new value you would have 11 samples. For the 11 samples you can run it again, and you can add another one, 12th value, 13th value, and so on, and you can continue until you get a better solution or your number of iterations are finished or so on, right? So this is all for the today's lesson. We can finish the lecture today. Okay, if you have any questions you can ask.